Welcome back to this next video in which we are discussing dual vector spaces. Okay, so we have now defined a scalar multiplication rule on our dual vector space, and we want to make sure that this scalar multiplication rule obeys the relevant axioms so that our dual vector space is truly a vector space over the field capital F. Okay, so we've now checked closure. The next axiom that we need to check is associativity. Okay, so let me write this out here. So axiom number 2 then. So axiom number 2 is associativity of scalar multiplication with field multiplication. Okay, so for all C1 and C2 that you can pick from the field capital F, and for all, let's say, phi that you can pick from the dual vector space, it must be the case that C1 scalar multiplied with C2 scalar multiplied with phi is equal to C1 multiplied by C2 in the field, and then the answer scalar multiplied by phi. Okay, so this is what we need to prove. So let's just put a bit of colour on here. So this is scalar multiplication in the dual vector space. This is scalar multiplication in the dual vector space. This is scalar multiplication in the dual vector space. On the other hand, this multiplication of C1 and C2, these two scalars in the field, that is multiplication in the field. Okay, so this rule is associativity of scalar multiplication with field multiplication. So it basically says that either you can firstly scalar multiply the element of the dual vector space, the covector here, by C2, get some answer which is another element of the dual vector space, and then scalar multiply that by C1 and get some final answer there. Okay, so scalar multiply twice. Or you can firstly multiply C1 and C2 together in the field, get some other scalar in the field, and then scalar multiply that with phi. And the answer needs to be the same, basically. Do it either way, and we want to get the same answer. Okay, so this is the associative law, the associativity of scalar multiplication with field multiplication here. Okay, so we need to prove that the two mappings that you would get, which will map the vector space capital V from, will map the elements of the vector space capital V onto the field, are going to be identical from these two different ways of doing it. Okay, so let's do so. So we want to prove that C1 scalar multiplied with C2 scalar multiplied with phi acting on a vector V is the same as C1 multiplied by C2 scalar multiplied by phi, all acting on the vector V. Okay, and I'll add the colour in once again. So we'll have scalar multiplication in our dual space, scalar multiplication in our dual space, scalar multiplication in our dual space, and multiplication in the field F. Okay, so we want to prove that this is going to be true for all V is an element of our vector space capital V. Okay, so how are we going to do this? Well, we're just going to take both sides and try and prove that they're equal to one another using the definition. So we'll firstly use this here. Okay, so we have got C1 scalar multiplied by some element of the dual vector space. So C2 scalar multiplied by phi. Ignore the fact that this is made up of two things at the moment. Just view it as an element of the dual vector space. Okay, so if I just underline this in yellow, view this as one covector in the dual vector space. So after all, if you worked out the answer to that, it is just a linear map in the dual vector space. Okay, then what we've got is C1 scalar multiplying this linear map, and then we're acting that on the vector V. Okay, well, just applying the definition here, this is going to be equal to C1 multiplied by C2 scalar multiplying phi of V, like so. So I'll put in the symbols here. So this will be multiplication in the field here, and this will be scalar multiplication in the dual vector space. So we're just applying the definition. So we've applied it once now, and now we're going to apply it a second time. So if we're now considering C2 scalar multiplied by phi acting on V, again we can apply the definition here and say that this will be C1 multiplied by C2 times phi of V, like so. Okay, where all of these multiplications now are done in the field, so this is all multiplication in the field. Now, What we're trying to do, remember, is we're trying to turn it into this. So what we're going to now apply is associativity of field multiplication. So we've got C1 multiplied by C2 multiplied by V, with the brackets around C2 and phi of V here. Okay, what we're going to do is we're going to take the brackets away from there and put them around C1 multiplied by C2, applying the fact that field multiplication is associative. Okay, so we'll end up with this, where the symbols again here are just pink. And now what we can do is apply the definition in reverse again now. So this definition here, we'll apply it in reverse. We've got C1 multiplied by C2. That's just some element of the field. So whatever this is, it's just some element of the field. We've got that scalar multiplying phi of V. That's just the definition of C1 multiplied by C2 in the field, scalar multiplying phi acting on V. Okay, so I've taken this side and turned it into this side, so I can put equal signs to all of these transitions. Okay, so that's how you prove then that scalar multiplication does indeed associate with field multiplication for this scalar multiplication that we've defined on the dual vector space. Okay, so associativity is now proven. Let's go on to the identity criterion. Okay, so the third axiom that we want scalar multiplication to obey in any vector space concerns the multiplicative identity element of the field, capital F. And it says that if you scalar multiply any element of the vector space, so in this case any covector in the dual vector space, so for all phi is an element of V star, we want it to be the case that 1 scalar multiplying phi is equal to phi. So we want it to be the case that if you scalar multiply any covector by 1, you get that same covector back again. Okay, and 1 here is the multiplicative identity from our field, capital F. Okay, so we want it therefore to be the case that 1 scalar multiplying phi of V is equal to phi of V. Okay, where I'll just put in that turquoise dot there. This is scalar multiplication in the dual vector space. But now what we can do is just apply the very definition of scalar multiplication in the dual vector space. Okay, so the definition says that this is just take 1 and multiply it in the field with phi, phi of V. Okay, so work phi on V, get the answer which is in the field, and then take 1 and multiply it by that answer. And of course 1 is the multiplicative identity in the field, so of course this will just equal phi of V, whatever that is equal to, because by definition the multiplicative identity in the field multiplies by any other element of the field to give that other element of the field back again. So indeed we do get that this is just going to be phi of V. Okay, so there's the proof of that. The multiplicative identity in the field does indeed scalar multiply any covector in the dual vector space to give that covector back again. Okay, so now axiom number 4, the two distributivities. So there are two parts to axiom number 4 that scalar multiplication must obey. Part 1 is the first distributive law and part 2 is the second distributive law. Okay, so the first distributive law is where you have 1 scalar from the field and 2 vectors from your vector space. So let's say for all C is an element of the field, capital F, so take any element of the field, capital F, and take any 2 vectors from your vector space. In this case we'll take phi1 and phi2 from the dual vector space here, so for all phi1 and phi2 that you can possibly come up with from the dual vector space, it must be the case that if we consider what C scalar multiplying phi1 plus phi2 is equal to, where all of these operations, the scalar multiplication here and the addition here, is done in our dual vector space, this must equal as a function, so this is going to be some function in the dual vector space, this must be as a function equal to C times phi1, where again this is scalar multiplication here in the dual vector space, plus C times phi2, where again this is scalar multiplication in the dual vector space, and this is addition in the dual vector space. And this then is a function acting on a vector in our original vector space, capital V, which we'll call little v. So we want it to be the case that this thing here, c times v1 plus v2, is equal to c times v1 plus c times v2. We want scalar multiplication to distribute over addition in the dual vector space. Okay, and that exactly means making sure that these two functions are identical to each other. Okay, so how are we going to do this? Well, once again, let's start with the left-hand side and see if we can turn it into the right-hand side here. Okay, so firstly, applying the definition here. So we've got scalar multiplication as the most outer portion here. So let's apply the definition for scalar multiplication firstly, where we're viewing v1 plus v2 as just being some element of the dual vector space. Okay, so again, we're going to apply our trick and just think of v1 plus v2 as being a single element within the dual vector space. So it is a single element within the dual vector space. So imagine that you've already worked out what that is, and now you've just got c scalar multiplying that. If we apply the definition for what that is, it's going to be c multiplied in the field with the answer to v1 plus v2 of v. Okay, so that's just applying the definition of how scalar multiplication was defined to work in our dual vector space, and that addition there, that's still addition in the dual vector space. Okay, so that's dealt with that scalar multiplication. Now what we can do is apply the definition of addition of two covectors in the dual vector space. Okay, so we've now got v1 plus v2 of v. Just by definition, what's that equal to? Well, we'll leave the c with the multiplication there in the field, and now v1 plus v2 of v will just be v1 of v plus v2 of v, where this addition here is going to be addition now in the field. That's just applying applying the definition which we gave for addition of covectors in the dual vector space. Okay, now everything there is just in the field. We've got c multiplying v1 of v plus v2 of v, where all of these operations are done in the field, and field multiplication obeys distributivity. Multiplication distributes over addition. So what we can do is rewrite this as c times v1 of v plus c times v2 of v, like so. Okay, where this is still multiplication in the field, this is addition in the field, and this is multiplication in the field. So all we've done there is apply the axioms of field theory, left distributivity in field theory. Okay, right. Now what we can do is start to reverse all of this. We're going to start to apply the reverse that we did here. Here we were using the definitions of scalar multiplication and addition in the dual vector space and turning them into what they were in terms of field addition and multiplication. Now we're going to go in reverse. We're going to take our addition and multiplication that are in the field and turn them back into scalar multiplication and addition in the dual vector space. So firstly what we're going to do is turn each of these into the element, the covector here, scalar multiplied by c. So this will be c scalar multiplied by v1 of v, okay, where now this is scalar multiplication in the dual vector space, and then we'll leave the addition for now, that's still in the field here, and we'll add it to c scalar multiplied with v2 of v, like so, where again this is scalar multiplication now in our dual vector space. Okay, so we're almost there. Now what we can do is apply the definition of addition in the dual vector space in reverse, and we can turn this into exactly what we've got up there. Okay, we can say that this is equal to c scalar multiplied by v1 plus c scalar multiplied by v2, where all of those operations are done in the dual vector space. We've gone nicely round in a circle here and got to the other side. Okay, so that's how we can prove that scalar multiplication does indeed distribute over addition in the dual vector space. Now finally, part 2, the second distributive law, and this is about how scalar multiplication distributes over addition in the field. So in this one you need two elements of the field, so we'll have C1 and C2, which are elements of the field capital F, and we also need an element of the vector space. So in this case we're in our dual vector space, so we'll have phi, which is an element of v star here. So pick two elements of the field, C1 and C2, pick a covector from the dual vector space phi, and now what we want to prove is that if we have C1 plus C2, where these two are being added in the field. So this is addition in the field, and we take the answer to this. So we take C1 and C2, which are both elements of the field, we add them together in the field. That's something we can do. We'll get another element of the field, and we then scalar multiply that element of the field with our covector phi, according to scalar multiplication in the dual vector space. Okay? The second distributive law says, and you can probably guess what it's going to say, that this is equal to C1 scalar multiplied with phi. Okay? Like so. Okay, plus, and now this is addition in the dual vector space here, so this is a turquoise plus, C2 scalar multiplied by phi. Okay, so these two maps have to be the same, and that will be scalar multiplication in the dual vector space. So this is a map from the vector space capital V to the field capital F. This is a map from the vector space capital V to the field capital F. We need to make sure that they're the same. That's what we need to check if we're going to check this distributive law. So what I'll just imagine doing is sticking in this is a function of V, and the same for here. This is a function of V. So we want to make sure that these two functions of the vector space capital V to the field capital F are exactly equal to one another for all little v is an element of capital V. Okay, so once again we'll take the left-hand side and turn it into the right-hand side to prove this. So let's start with the left-hand side here. So we've got some element of the field, and again we're just applying this trick of saying this is just some element of the field. Don't worry about the fact that it's two things added together, just view it as a single element of the field. This is just some element of the field. So we've just got some element of the field, scalar multiplying a covector in our dual vector space. We know exactly what the definition of that is. Okay, so this is just going to equal C1 plus C2, where that addition is still done in the field here, so I'll just colour that in purple there, multiplied in the field with phi of v. So you work out what v sent to by phi, and then you just multiply it by this scalar according to field multiplication here. Okay, that's just the definition of how this scalar multiplication works in the dual vector space. Then, of course, what we can do is we can apply right distributivity this time in the field. Okay, so we've got two things added together here, and then they're being multiplied by this. Okay, now what we can do is just multiply this out and turn this into C1 times phi of v, where that's multiplication in the field, plus C2 multiplied by phi of v, where the addition and the multiplication are all in the field. So this is in the field, this is in the field, this is in the field here. Okay, right, and then again we're now going to apply the definitions the other way round to what we did here. Okay, so we're going to go back into scalar multiplication and addition in terms of the dual vector space. So what we can now say is C1 times phi of v, where this multiplication's in the field, that's the same as doing C1 scalar multiplied by phi in the dual vector space, acting on v. Okay, and then adding it still in the field to C2 scalar multiplied by phi acting on v. Those two things are exactly the same. So just colouring this in, we've got scalar multiplication in our dual vector space there, and this is still addition in the field. And then it's just one final step. So now applying the definition of addition in the dual vector space in reverse this final time. This is the same as this. We can bring these two things and add them together in the dual vector space, and then take that final function, act that on v, and that's going to be exactly the same as this, and therefore, because of all these equal signs, it's equal to this side here. So indeed, this final distributive law does hold true. Addition in the field is distributed over by scalar multiplication. Okay, so we have now then checked that this set of all these linear maps from your vector space, capital V, to the field which that vector space is over, capital F, this set can have a very natural addition law and a very natural scalar multiplication law by the field capital F put onto it, and therefore you can build it into a vector space structure. This vector space is known as the dual vector space of your vector space capital V. So you give me any vector space over any field capital F, I can instantly construct you another vector space over that field capital F, which is the dual vector space known as V star, and this is well defined, and this is known as the algebraic dual vector space, or just the dual vector space, or even shorter, the dual space. Okay, now, I'm not going to do an example in this video. What I'm going to do is have another video, which will be the next one along in this playlist on vector spaces, which will be entitled Bases of Dual Vector Spaces, and then at the end of that we'll have a look at an example of taking the dual vector space of a vector space. Okay, so we'll end this video here.